Good evening to everyone. Good evening to everyone. Today, Dr. Jan is going to talk us about the bone marrow transplantation from beginning to today.
Yes.
Thank you.
Good evening from my side to everybody. I hope today it's a bit easier for you to listen to me because it's not that fulfilled with biochemical pathways, and it's more like some historical tales what I'm prepared for today. So maybe we can have the next slide, Sandeep. Yeah. So there was an in the ancient medicine, let's say about the first or second century of Christian time, there was a knowledge in medicine that bone marrow has something to do with blood production. And there are some reports from Arab and Egyptian and Greek doctors who tried to cure patients who had bone marrow failure syndromes or at least too less blood, let's say it that easy way. And with the suggestion that the patients should eat bone marrow from sheep or from cows. Of course, this was not helpful. I don't know if in Indian medicine this was a knowledge at the same level, but as far as we learned in the last years, that the connection between the Greek and Arab and the Indian world was much closer than we ever believed. So I guess the same knowledge was presented in Indian countries in that time. The first step to modern hematology was the discovery of the blood group system, ABO. This was done by Karl Landsteiner in the year of 1900 after Christ. He was rewarded with the Nobel Prize for Medicine for that detection. And with this knowledge, it became possible to do blood transfusion between humans without any reaction. So this was the first step to scientific hematology at all. Could you give the next slide, please? And then after the Second World War, in the consequence of the atomic bombs in Hiroshima and Nagasaki, where not only many people died because of the explosions, but many died because of bone marrow failure, which was due to the radioactive fallout, which was produced by the atomic bomb. So the medicine focused a little bit on how to deal with these patients, and the science focused a bit about what is radioactivity and irradiation is producing in man and animal. So one of the scientists named Jacobsen, he was a Danish scientist, made an experiment with mice, and he irradiated mice with doses of radioactivity, which leads to bone marrow failure in mice. And all mice died due to bone marrow failure. But when he protected a little part of the leg, on the bone of the leg, or he protected parts of the spleen, the mice survived, and the bone marrow was repopulated by a normal bone marrow. So it was a very strong discussion going on. What is the reason for that? And in the end, it was understood that some cellular, some cells from the shielded bone or from the shielded spleen were able to move to the destroyed bone marrow and start a repopulation of the bone marrow at that time. So next slide, please. No, one step back, please. Sandeep? No. Can you get? Yeah. The next important step in direction of successful bone marrow transplantation was done in 1952. The situation was that some workers in a nuclear power plant from Yugoslavia had an accident and were confronted with radioactivity, which led to bone marrow failure. And these patients were brought to Professor Maté in Paris, and he tried to treat them. And he tried to treat them with bone marrow transplantation. And he transfused them bone marrow from family donors. But in the end, successfully, unfortunately, 4 of these 6 patients recovered, but none of these patients showed any sign of engraftment of the transfused bone marrow. Those who recovered had a spontaneous recovering of their own bone marrow function. And so the transplant was not successful. In 1955, Don Thomas tried to transplant patients with leukemia from family donors, but this was not successful either. So there was a very big disappointment, and there was a feeling that bone marrow transplantation is not working in men. Next slide. During the end of the 50s, there were done about 200 transplants in patients, and none of them was successful. Professor Maté tried to cure 1 patient with leukemia and transfused at the same time bone marrow from 6 different family donors. And 1 of the family donors showed engraftment in the patient, but the patient died due to infectious complications. So next slide. Yeah, the real transplant success story started in 1958 when Paul Doucet discovered the system of the human major histocompatibility complex, the human HLA system, and made it possible that we can look for matching bone marrow donors in the families of patients. And then, next slide. The first successful transplantation took place in a child at the same time in 2 childs, 1 in Minneapolis and 1 in Paris, who had a disease which is called thymic lymphoplasia and agammaglobulinemia at that time. And the reason, nowadays we would say these children had a SCID disease, severe combined immunodeficiency, due to an ADA deficiency. At that time, there was no difference known between ADA1 and ADA2. They only was known that there's an ADA deficiency at that time. And why was it possible to make a transplant successful at that time in ADA patients? One reason is that patients with an SCID don't have working T cells, as I showed in our last lecture, and they don't need chemotherapy and conditioning regimen for the engraftment of the donated bone marrow. Because the T cells are not working, there's no rejection. And that is one of the main reasons that the transplant in SCID patients started to be successful. So, and if you're from Europe, you say the first transplant ever took place in Paris. If you're from the US, you say it was in Minneapolis. And if you're from the rest of the world, you can decide whom to follow. Now we step a little bit aside because we had last week discussion about ADA2 deficiency. So I make some comments on ADA and the kind of working of ADA. And then we have to look to a very special molecule in the body, that is adenosine. Adenosine has a very big task in our body, and adenosine is part of the one of the modules from DNA and RNA, but it's even more important as part of the ATP. This is adenosine triphosphate. Can you show the next slide, please? And adenosine triphosphate is the carrier of any energy in our body. So if a muscle cell is contracting, ATP is the molecule who's presenting the energy for it. Or if a nerve in our brain is sending a signal to a neighbor cell, then ATP is providing for the energy to do that. And the energy is situated in the phosphate molecule, which is connected to the adenosine. And if you set the phosphate molecule free, then the energies can be used for any enzymatic or, let's say, muscle cell to do their action. And we do have very much adenosine ATP in our body. Some biologists figured out that we produce half of our body weight in ATP every day. So this is a very active substance, and it's present in very many different ways in the metabolism of all our cells. And we need, in our cells, we need to have a very balanced way to deal with adenosine. The next slide. So if the cell needs to inactivate adenosine, it uses an enzyme which is called ADA, or adenosine deaminase. And deaminase is putting out the amino part of the adenosine, and then it's ineffective anymore. So next slide. This is a bit complicated. Can you push one more? There are several cells in our immune system who are using different ADAs. And the normal effector T cells use, one more please, ADA1 for the cell reproducing. And if you're in effector T cells, ADA1 is active. And if ADA1 is missing, then we have an overload of adenosine in the T cell. And this stops the production of DNA because we need other modules for the DNA production, mainly guanine. And the production of guanine is stopped in the cells when adenine is in the overload. So patients with an ADA1 deficiency are not able to produce T cells and get a lack of T cells, though they have a SCID. And next slide, push again. Yeah. And some other cells of the immune system use ADA2 to stop the effectivity of adenosine. And these are cells from the granulopoiesis and other immunocells. So if you have a defect of ADA2, the phenotype of the disease is much more different. Next slide. Next slide. So if you have, just to repeat, if you have the disease of ADA1 disease, you have a SCID without any T cells, the patients die in the first month of life due to viral infection complications. They don't have any NK cells. They have B cells, but they are not able to produce immunoglobulins because, as I showed you in the last lecture, B cells are only active when they get activated by functioning T cells. So if you have a lack of T cells, then the B cells are not working anymore at all. Next slide. Yeah. If you have the ADA2 deficiency, you have an excess of pro-inflammatory activation in our tissues because there's a lack of regulation of inflammation, and we have signs of immune dysregulations like autoimmunity reactions, and we have defects in our bone marrow function. On the right side of our of this slide, you can see there are some. Is a study about 58 patients with ADA2 deficiency, and many of them have some immune dysregulation. Many of them have inflammatory and vasculitis problems, and a few of them have bone marrow failure symptoms. But you can see this is what the picture wants to show. There are no hematologic problems alone standing in ADA deficiency. There are always patients, the only patients who have a combined problem with immune dysregulation and hematologic problems, or inflammatory problems and hematologic problems, or even problems in all of these disease components. So this is what ADA2 is dealing with, and these patients are very much more complicated to transplant because they have some immunity and T-cell functions. So you need conditional regimen, and you have to control the inflammatory activity. And this is just to complete the discussion we had last week about the ADA2 patient, which is now transplanted in your institute. Next slide. So after the first successful transplant in 1968, the transplant field was very much growing. In 1972, the first reports from Seattle Fred Hutchings Center were published, where more than 20 patients with acute leukemias were successfully treated by bone marrow transplantation. And Seattle, under the director of Don Thomas, who was rewarded for his work with the Nobel Prize as well, became the, let's say, the most important transplant center of the world. And everybody who was involved or wanted to get involved into this field wanted to spend some time in Seattle to learn from his team at that time. And one of the most important things the group in Seattle started was that they developed an animal model for transplantation, where they used dogs, where they transplanted bone marrow in dogs. Before that, it was done only in mice as an animal model, and mice don't live that long. So when you transplant dogs, you can study the effects and the problems of transplantation over a longer time. And so they learned in their animal models what is about GVHD and what is about chronic GVHD. And they could study in their animal model with dogs the effect of cyclosporin and methotrexate to prevent acute and chronic GVHD. And this is still the backbone of our immunosuppression therapy after transplant. So this was developed in Seattle at that time, and is still the threshold of every treatment. Next slide. But there were severe problems. One I mentioned already, acute and chronic GVHD occurred in a great deal of patients, and transplant could only be done in 1/3 of the patients because of the lack of sibling donors. And the conditional regimen which was needed led to high toxicity and treatment-related mortality and long side effects of the treatment and long time damages. And at that time, it was not possible to think of transplantations beyond the disparity of the HLA system. So next problem. So what happened? One thing is that donor registries started to come into existence, of course, at DKMS in 1991. In England, it was the Anthony Nolan program, and in the United States, the National Marrow Donor Program. So this was the attempt to have more to find matching donors for every patient and to get transplantation available for a greater deal of patients. Next slide. Then transplantation was used for other diseases. And the first patient with thalassemia major who was transplanted in the same city as the leukemic patient in Seattle by Don Thomas was done in 1982. And then in Minneapolis, the first patients with an inborn errors, these are, let's say, metabolic diseases where one enzyme in the metabolism is not working or missing. And there are some of these metabolic diseases in which monocytes can carry and produce this missing enzyme. And if you do a bone marrow transplantation, then the donor monocytes have the capability to migrate into the tissue and supply the lacking enzyme and stop the metabolic disease. This is done, for example, in adrenoleukodystrophy or Hurler syndrome. These are two metabolic inborn errors where one enzyme is lacking, and there are toxic products accumulating in the brain, and this leads to neurodegeneration, and the patients die due to neurodegeneration, and this degeneration can be stopped with a successful transplant from a healthy donor, but it's still only for a few patients and still very complicated to do. And one big step to progress, excuse me, one back. One big step to progress for transplantation was the switch from the HLA typing of the unrelated donors. There was a switch from the testing from serology to examination of DNA base and more sensitive testing. So the donors, the unrelated donors, matched very much better than only after serologic testing. So this was a great deal and a great step forward for the transplantation. Next slide. And in the transplant units, the first transplants were done with either busulfan or TBI as the backbone of the transplant regimen, conditioning regimen. And this is very toxic, especially for elder patients. So there was started a development to use less toxic and reduced toxic conditioning regimen, like took only the half doses of busulfan and introduced other chemotherapeutic substances, which reduced toxicity. And one very big step forward was the improvement of the supportive care, let's say better treatment of an infection, prophylactic treatment of fungal infection, prophylactic treatment of viral infection, the development of antiviral drugs. And another step forward was in the beginning of the transplant, the patients were situated in live islands, so they only had their bed and were closed from their surroundings completely, and which was a very stressful situation for them, and it's completely different to what we have now, as you have in your institution, open rooms and HEPA-filtered air in the complete room. So this was another big step forward. Next slide. What to do about the transplantation beyond HLA borders? So there were two concepts to overcome this problem. One is to use cord blood from as a bone stem cell source, and the second one is to use highly purified stem cells from a not matching donor and give them a high dose of these stem cells. So, next slide. This started with manipulation of the selected stem cell from the peripheral blood. So if you collect stem cells from the peripheral blood, next slide. Yeah, you end up with a high dose of T cells in the product, which was believed not to be practical in haploidentical transplant because of the end of big problems in acute and chronic GVHD. But there was a technical device developed which was able to reduce the T cell count in the bag from 10 to the power of 8 to 10 to the power of 3 per kilogram body weight. So the risk of GVHD was very much reduced. And this was done, next slide, by a technique with magnetobeads. This is the red ones are the CD34 positive stem cells. I don't know if you remember in our last lecture, I told you that every hematopoietic cell has special epitopes on the surface, and the hematopoietic stem cells carry the epitope CD34, and these epitopes are covered with antibodies against CD34. And these antibodies against CD34 are combined with some iron particle. And then our whole stem cell bag is set in a device where it runs through a metallic column. And this metallic column is set into a magnetic field. And as long as the magnetic field is working, the iron part of the antibody sticks to the column, metal column, and the stem cells are resting at the column, and the rest of our stem cell bags are passing. And after that, you can reduce the magnetic field and elute the stem cells from the column and have a highly purified stem cell collection. And then you can give a high dose of purified stem cells, let's say about 12 to 20 million stem cells per kilogram body weight of the patient, and that is able to overcome the HLA borders. So next slide. The pro for these purified stem cells from haplodonors was that the donor availability was great because you could use non-matching family members or haploidentical parents to transplant for children. When you transfuse such a high dose of stem cells, it ends up with a very short regeneration time and no prophylaxis, GVHD prophylaxis was needed because we have highly depleted the T cells. The problems is of this system, it takes a long working time in the lab to purify the stem cells. This is about 36 to 48 hours pure work in the lab. It's very expensive, and if we reduce the T cells in our product, the T cell regeneration is very much delayed for a long time, which increases the risk for any viral or fungal infection in the course of transplantation. The problems, the advantage of these, if you use cord blood, is you can use not really good matching cord blood as a stem cell source, and the new immune system is not causing very many problems with GVHD because these very young cells, it's believed that they are more likely to accommodate in their new surroundings. But these stem cell amount in cord blood product is very low. So only, let's say, 100,000 or 200,000 cells per kilogram of the patient weight. So it takes a very long time until you can see any recovery of the donated bone marrow in the patient. And there are only a few cord bloods. So we have only very little access to cord blood donations. And it's hard, it's only a very limited availability. So next slide. And then there was the latest breakthrough, and Europe benefiting from that. It was believed for a long time that haplodonor transfuse of haploidentical stem cells or bone marrow will end up in a very high rate of non-treatable GVHD reactions. And in a new concept, it was shown that this is not true. When you transfuse the non-selected bone marrow or stem cells haploidentical into a patient, then the immune system of the donor and the immune system of the recipient are highly activated and fighting against each other. And then you can stop this activated immunofight, let's say so, with high dose therapy with cyclophosphamide. And then this made it possible that the non-matching graft is not rejected, and the non-matching graft is not causing severe GVHD. So this this technique in Europe, it was introduced from Bacigalupo from Florence. I don't know if it was introduced in the US at an earlier time point, and I'm not aware of this, but maybe. The advantage is that you can use haploidentical donors. There is no need for purification of the stem cells. You just can transfuse your bone marrow or the collected stem cell as you get it. And in the meantime, you have a secure engraftment and a level of GVHD which is controllable. So this made it possible to give access to transplant from haploidentical donor in many transplant centers who are not working with much laboratory capacities in countries with not such a high income like in Europe. Next slide. So this is the state of the art from today, and what may be the future. To have an impression what the future will bring, we have to understand that stem cell transplantation is in the tension field with any other possible treatment for the diseases we treat. So if we see improved conservative therapy, then the indication for stem cell transplantation might be delayed. Let's say if for let's say for thalassemia patients, for example, if it's possible to have a transfusion program which is supporting them on a secure way and can control the iron overload, which is a consequence of their heavily transfused many transfusions, then the patients can live a normal life for a long time, and maybe they don't need to go for the risk of transplantation. Or in thalassemia patients, it might be possible in the future to a greater deal of patients to use gene therapy. So they don't need to transplant because this gene therapy is helping them out of the way. It is possible nowadays, but the therapy costs are very high, up to $1 million. So, but maybe in the future it's getting cheaper and available for more patients. And in some ways, enzyme substitute therapy might be possible in metabolic diseases. So for ADA1 patients, for example, there exists medication providing ADA per IM injection. So it's not working that very well in the patients yet. So it's still better for them to get a transplant, but maybe in the future we find ways to treat them without transplantation. And on the other side, those who are involved in the field of transplants are thinking how to reduce the toxicity of our conditioning regimen. And there are some teams in the world working, for example, to try to have a myoablative therapy without chemotherapy. One idea is that it's possible to produce genetically modified T cells who are attacking special antigens on any cell. So this is used already for the treatment of leukemic patients, and it's called CAR T cell therapy. These genetically modified T cells in leukemic therapy are attacking one epitope which is presented by the leukemic cells. Now it's used for the cells against CD19, but it's theoretically possible to produce those CAR T cells who are aiming at CD34 antigens. So it's possible to make a myeloablation with CAR T cell activity in the donor. So maybe this is one way to go in future. Next slide. I think that's the end. Yeah. Thank you very much. So I'm happy to take your questions.
Any questions?
If there are no questions, I have a layman question, Jan, and I hope it's not completely senseless.
Yeah.
You were saying on your last slide that gene therapy may be an option for the future, so that stem cell transplantation is no longer required.
Yeah. Sorry?
In
thalassemia patients. Yeah.
In thalassemia patients. Okay.
Yeah.
That was the bit I didn't get, because to my understanding, transplantation is still part of the gene therapy, right? But it's
yeah.
Okay.
But,
okay.
Yeah. So we can talk about gene therapy. What is happening in gene therapy is, in thalassemic patients at least, is if you are a fetus in the mother's the placenta of the mother, you're using different HB than as an adult patient, and the fetal hemoglobin is called HbF, and it doesn't use beta chains in the HB. It's using alpha and gamma chains in the HB. And in the early days after the birth, the HB production changes from HbF to HbA2. And what you're doing in gene therapy right now is you're collecting stem cells from the patient and then knock out the regulation part, which controls the change from HbF to HbA2. So those genetically transduced cells are producing HbF. And then you can reinfuse these modified stem cells to the patient, and they can produce HbF. So the beta thalassemia in that way might be cured. But you need to have these transfused modified stem cells to populate in the patient's bone marrow, and therefore you need some conditional regimen, which is busulfan right now, so that the modified stem cells can expand and produce HbF. So it's still some way of transplantation you're using in gene therapy.
Thank you.
Yeah.
Is there any question from others? Okay, sir, then I think no questions.
Okay.
Thank you.
Thank you very much to all.
No, sir. Thank you for the
We'll meet on
class.
next.
Okay.
Yes.
Thank you. Have a good evening.
Bye-bye.
Thank you. Bye-bye.